So, let us start on the next part of the talk. So, where we shall be discussing about again or continuing about what we were talking in the last class on field isomorphisms. In particular, we shall be trying to see how we can construct these transformations in a more algorithmic manner. Okay. So, I shall be starting with like defining of course, like as we have seen on isomorphisms, but also on a term which is called as composite fields. Okay. So, and we shall see how we can develop isomorphisms between the composite fields, and as I said, like how we can algorithmically construct these isomorphisms. Okay. So, I shall state two broad algorithms, and and the final algorithm is more efficient compared to the first one. Okay. So, therefore, what are composite fields? So, as we have seen fields of the or extension fields of the type of GF2 power of n, okay, we can also construct fields of the type of GF2 to the power of n whole power of m. So, these kind of fields are called as composite fields. So, if there exists irreducible polynomials say qy of degree n, then I can use that qy and construct a field GF2 to the power of n from GF2, and then I use a polynomial px of degree m, okay, which are used to extend GF2 to the power of n to GF2 to the power of n whole power of m. Okay. So, therefore, right, I extend from GF2 to GF2 to the power of n using qy, and I extend GF2 to the power of n to GF2 to the power of n whole power of m using px. So, now the composite field, which is denoted as GF2 to the power of n whole power of m, you can easily understand that if I consider another field say GF2 to the power of k, where k is equal to m into n, that is the product of m and n, then the number of elements in GF2 to the power of n whole power of m and GF2 to the power of k are same, they are equinumerous. Okay. So, therefore, right, if I can establish a one-to-one homomorphism between them, then that qualifies as an isomorphism. So, I can establish an isomorphism between these fields. I can establish an isomorphism between GF2 to the power of k to GF2 to the power of n whole power of m, and also vice versa. So, I can transform an element from this field to this field, and also from this field back to GF2 power of k. So, this can actually give rise or give opportunities for efficient implementations, where I have got an original field say GF2 power of 8, say k is equal to 8. I transform this into say n equal to 4 and m equal to 2. So, I transform this into a field GF2 to the power of 4 whole square, and I do my computations in this field. So, as I will see, or we will see in more details in subsequent classes, that means that I can now do the computations, right, or the fundamental computations in GF2 to the power of 4, which is a much more simple field compared to GF2 to the power of 8. And once the result is done in GF2 to the power of 4 whole square, I can get the result back to GF2 to the power of 8 by using my reverse transformation. I can do further decompositions, that means I can decompose GF2 to the power of 4 further into GF2 square, and I can get a field which is like GF2 to the power of 2 power of 2 power of 2, which is also would be isomorphic to GF2 power of 8. Okay. So, how do we construct isomorphism between composite fields is what we shall study in today's class. So, if you remember, like we discussed about primitive polynomials. So, therefore, right, these primitive polynomials will be used to construct say GF2 to the power of n, which is denoted as say qy. Okay. So, note that primitive polynomials are also irreducible, as we have discussed. So, therefore, right, it essentially can be used to extend the field GF2 to GF2 power of n, and suppose, right, omega is the root of this primitive polynomial. So, note that if it is a root, then it is also a primitive element. So, therefore, now the elements 0, 1, omega, omega square to the power of omega to the power of 2 to the power of n minus 2 will therefore give all my elements in GF2 to the power of n. Okay. You can think of the example that I gave you for GF2 to the power of 4. So, that had all like 15 non-zero elements. In a more general setting, there will be 2 to the power of n minus 1 non-zero elements, and of course, you have 0. Likewise, you can also use the primitive polynomial to construct GF2 to the power of n whole power of m, and as I said, we denote it by px. Okay. So, let alpha be the root of this, and now the elements will be 0, 1, alpha, alpha square, so until alpha to the power of 2 to the power of nm minus 1. Okay. So, now I have got all the elements say in GF2 to the power of nm, and there are totally 2 to the power of mn elements in this field. So, So now the arithmetic, I want to define arithmetic in the field gf2 to the power of k, which is my original target field, where k is equal to m into n. Now this can be performed by modulo the primitive polynomial Rz. Okay. So what is Rz? Now Rz is nothing but z to the power of k plus rk minus 1, z to the power of k minus 1 plus so on till 1. Okay. Where each of these Ri belongs to gf2. That means they are either 0, 1 elements. So again, if gamma is a root of this polynomial, then elements can be expressed in the polynomial basis like 1 gamma, gamma square, so on till gamma to the power of k minus 1, in like as we have seen in the previous discussions. So how do I map gf2 to the power of k to gf2 to the power of nm, where k is equal to mn? A very simple method to do this conversion is to find the primitive element of both the fields. So gf2 to the power of k and gf2 to the power of n whole power of m. The primitive elements are say gamma and alpha, which means like gamma is a primitive element of this field and alpha is a primitive element of this field. Okay. So now what I will do is that I will make a check. If you remember the example that I gave you, exactly like that, I will check that, of course, like since gamma is a primitive element, it has to satisfy r of gamma equal to 0, because it is the root of the polynomial Rx. Okay. And r of alpha, that means this element where I am mapping gamma to alpha. Okay. So therefore this alpha should if I plug in alpha to r, but now I have to do a modulo in the target field. Okay. So in the if you remember in the example, it was I was doing modulo f2. Okay. So here we have to do modulo of px qy, because there are two polynomials on which you have to function. Px will be your bigger polynomial, because you are essentially this will be of degree m, and qy will be essentially your degree n polynomial, which is essentially for working on your base fields or on the subfields. Okay. So therefore, right, if this satisfies, then you map gamma to alpha. Okay. And if the roots do not satisfy the polynomial, we repeat the test for the next primitive element. Okay. So you repeat it for the next primitive element. So once you have got that map, gamma and alpha, then you can essentially for all the 2 to the power of k minus 2 elements, which are essentially, for all the 2 to the power of k minus 1 non-zero elements, you can define mappings by just mapping gamma power of I to alpha power of I. Okay. So in that case, you basically map all the elements. Okay. So therefore the algorithm, right, for doing so, we can actually state this in an algorithmic fashion. So the input is n and m, qy, px and rz, which are my polynomials, and I want to map gf2 power of k to gf2 power of n whole power of m, where k is equal to n into m. So we find out the primitive element of gf2 power of k, which is denoted as gamma, and for alpha equal to 1 to alpha to the power of 2 to the power of nm minus 1, that means for all the possible elements in gf2 to the power of mn. Okay, I have to calculate, I have to check this, that is whether alpha is a primitive element in my target group and whether it satisfies this equation, that is r alpha mod of qy px is congruent to 0. The moment I get such an element, I can break and I essentially have got my alpha, and therefore I can establish my mapping for all the 2 to the power of mn elements. Okay, therefore I can map, I can calculate alpha power of I, calculate gamma power of I. Note that when I am doing calculation alpha power of I have to always do modulo of qy px. Okay, and my b1 essentially is gamma to the power of I mod rz. So this has been repeated twice, but anyway you can just keep it once. So basically gamma power of I mod of rz, and then I map a1 to b1. Basically I map an element a1 to b1 and I get all the possible mappings required. So let us see an example for that. So suppose I said I want to map gf2 power of 4 to gf2 square, okay, which is a composite field, and I said rz as z to the power of 4 plus z plus 1. My qy is y square plus y plus 1 and px is x square plus x plus 2. Note that here this polynomial is an irreducible polynomial for gf2 squared. Okay. So the elements can be elements from gf2 square, whereas these elements are irreducible polynomials respectively for gf2 power of 4 and this for gf2 power of 2. So the elements are in 0 and 1 in gf2. So note that qy is used to construct gf2 square, while px is used to extend to the field gf2 squared. Okay. So the first primitive element is a gamma, which gamma which belongs to gf2 power of 4 is 2. Okay. That is, you can also represented by the polynomial x, okay, because it has got a binary representation which is 1 0, and therefore that stands for x. Now it can be checked that 2 can be used to generate all the non-zero elements of GF 2 power of 4, so it is a primitive element. Likewise, the first primitive element of GF 2 power of squared such that this condition that we were checking, that is Rz is congruent to 0 mod of Qy Px is true, is actually 4. Okay. So 4 would mean that essentially it is 0 1 0 0. Note that this is an element of GF 2 squared. So therefore, if I have got an element 0 1 0 0, then that would stand as essentially it means that the first part is 1, okay, and the second part is 0 0. Okay. So there are two parts in the expansion. Okay. So therefore, right, if this is true, then I will map 2 to 4, okay, and 0 will get mapped into 0. So all the other elements I will get mapped into, say, 2 square to 4 square, 2 cube to 4 cube, and so on. Okay. So in more details, so this is the proof that 4 indeed belongs to GF 2, which belongs to GF 2 square. This will be like GF 2 square. Okay. So GF 2 square is actually indeed the correct choice. So note that 4 is 0 1 0 0, and therefore this is nothing, 0 1 is x, okay, and this is 0 0. Okay. So note that this is not an element in GF 2 power of 4. If this was an element in GF 2 power of 4, then this would have been x square. I would have represented as x square. But this is an element of GF 2 square whole square. Okay. I have missed out this 2 here. It is actually GF 2 square whole square. So that means, right, in GF 2 square whole square, let me try to write here. So essentially that means that if I have got like an element, say GF 2 square whole square, okay, so it means that the polynomial or the representation is as follows. So that means, like, there are two parts of this decomposition. The first part is, say, A, the second part is also B, okay, is B, and therefore the element is actually Ax plus B, okay, where A and B both belongs to GF 2 square. Okay. So that means, right, if I have got A as 0 1, okay, so if I have got A as 1 and B as 0, okay, which are elements in GF 2 square, then this is what? This is nothing but x, okay, and that is what we have denoted here as x. Okay. So likewise, right, so now with this like background, you can verify that whether the condition that we had is getting satisfied. So I calculate Rx, and therefore Rx is nothing but x power of 4 plus x plus 1, okay, and we know that. So now interesting is that how we do the mod of Qy Px, okay. So you note that I have got x to the power of 4 plus x plus 1, okay, and x to the power of 4 plus x plus 1 needs to be reduced. So therefore I use first my polynomial, which is Px, okay. So in Px my polynomial was x squared equal to x plus 2 or x squared plus x plus 2. So if I set that to 0, I have got x squared equal to x plus 2. So 2 is an element of GF 2 square. So therefore x cube is equal to, if I just cube this, okay, so if I just multiply this with x, then I will get, and if I do again some simplifications. So note that the moment if I multiply this x squared with x, okay, so suppose I have got x squared equal to x plus 2, okay, and if I multiply this by x, then I will get x squared plus 2x, okay. But note that in this polynomial, in this representation, because I am talking about GF 2 square whole square, x squared is nothing but x plus 2. So therefore I will replace this with x plus 2, okay, plus 2x. So therefore, right, if I want to calculate this or simplify this further, I can take x common and then I add 1 plus 2, that is 1 gets added with 2 plus 2. Okay. Now note this math is essentially again done in GF 2 square. So, if I want to do 1 plus 2, that means it is nothing but 0 1 XORed with 1 0, okay, and therefore, I get 1 1 here, okay, and this 1 1 is nothing but 3, and that is why I have got here 3x, okay, and this 2 will come here. So, I get 3x plus 2, right. So, likewise, right, I calculate x power of 4, which is 3x squared plus 2x, make some simplifications, I get x plus 1, okay. So, therefore, right now you can observe that if I get so therefore, x squared is equal to x plus 1, okay, and this implies that R4, if I get R4, and like R4 will be equal to 0 mod px qy, because now I have to bring in qy into play, okay, and and therefore, right, I get this as 0, okay. So, therefore, right, I get x plus 1 here, which is my x power of 4. So, if I substitute x plus 1 here, then I get x plus 1 plus x plus 1, which is equal to 0. Okay. So, therefore, R4 is indeed equal to 0 mod px qy, and therefore, right, my condition is satisfied. Okay. So, therefore, keep in mind that when you are doing computations like 3 into 2 in GF2 square, then you have to express 3 as y plus 1, okay, and 2 as y, and therefore, when you are doing computations of say 3 y plus 1 into y, then you will have y that as y square plus y, and y square plus y is nothing but 1, because now your polynomial is qy. So, therefore, when you are doing the final step here, okay, so therefore, this 3 I multiplied with 2 and I like wrote 1 over there, because 3 into 2 in GF2 square with this irreducible polynomial is 1. Okay. So, this math we have to do in a little bit in a careful manner, okay, but if we do that, then we should be able to easily verify that this equation, this is indeed satisfied. Okay. So, so with this, okay, so therefore, right, let us try to go ahead and try to see. So, therefore, now once you have got this checked out, you know that 2 gets mapped into 4. You can take the power of 2 and power of 4 and again do similar computations, and you can develop a mapping for all the 15 non-zero elements, and I map 0 to 0. Okay. So, this is one way in which I can algorithmically develop an isomorphism between these composite fields. Okay. But at the same time, you can easily understand that for this particular construction, I was doing an exhaustive analysis. I was doing an analysis. So, if you remember the like the for loop counts, then you will see that the for loop essentially goes for all possible things, that it goes for all 2 to the power of mn values. Okay. And this is not very efficient when you are trying to do it for larger fields. Okay. So, there is an efficient algorithm for handling this. So, let me talk about that subsequently. So, here I want to present an efficient algorithm between binary and composite fields. I want to map GF2 power of k again to GF2 power of mn, where k is equal to mn, and I want to develop a 0 1 matrix. So, this is a k cross k matrix, which means that I can take any GF2 to the power of k element, multiply it with this matrix, and I should get back my resultant output. Okay. So, again let me try to explain this, which means that suppose now I have got T. Okay. So, this T matrix is now a k cross k matrix. So, this is what I want to construct out of the algorithm. Okay. And I take an element in GF2 to the power of k, and as you know that any GF2 to the power of k element can be expressed as a vector of dimension k. Okay. So, I can express it as a k cross 1 vector. So, now if I multiply this T matrix with this element in say GF2 power of k, right, I get another k dimensional result, but this k dimensional result now should belong to GF2 power of n whole power of m. Okay. So, that is the overall objective. So, I want to basically construct this matrix. Okay. So, this matrix, I will try to, of course, like if I can develop this matrix, then and if this matrix inverse also exists, then the inverse of this matrix will give me the reverse transformation from GF2 power of n power of m to GF2 power of k. So, the interesting thing is that rather than 2 to the power of k, which I was doing in the previous algorithm, this mapping I can develop by only mapping k elements, which are the basis vectors. I will just map only the basis vectors, and that should be sufficient. Okay. So, therefore, right, let us see about how we can do that, and like we should be able to do that in a much more efficient manner. So what I do here is that I essentially look at my polynomial basis for gf2 to the power of k, which is denoted as 1 gamma gamma square till gamma to the power of m minus 1, okay, where gamma is a primitive element of gf2 power of k. Okay, so therefore, right, I mean now and I find out the unity in both the, and for the first thing which I do is that I map the unity of both the fields. I map the one in the field gf2 to the power of k to gf2 to the power of n whole power of m. Now the one in both the fields is denoted by the polynomial 1. Okay. So therefore, right, we first map the unit element in gf2 to the power of k to the unity element in gf2 to the power of n whole power of m. Okay. And essentially, right, I mean that means that I have got one column of my matrix decided. Okay. So I will clarify that. So then what I do is that I find out the primitive element in gf2 to the power of k, the primitive element which we essentially, as we have discussed in the previous discussions. So I get, say, that element is denoted as, say, gamma. So now gamma is mapped into alpha power of t, okay, and alpha which is essentially the base element. Okay. So now what I do is that I map gamma to alpha power of t, and then I mapped gamma squared to alpha power of 2t, and likewise I continue this and I map gamma power of I to alpha power of it. Okay. That means I do this for all k values from 0 to k minus 1, I do it only for k values. Okay. And if I have done that, then my entire mapping is decided. Okay. So therefore, if I plug in I equal to 0, that stands for 1. So I have already mapped 1 into 1, and I start mapping, you know, like gamma power of 1, that means gamma to alpha power of I, okay, and I mean alpha power of t, and then I mapped gamma squared to alpha power of 2t, and likewise gamma to the power of k minus 1 to alpha to the power of k minus 1. Okay. If I have done that, then I have mapped all my basis vectors. So these are my basis vectors. Okay. Okay. So maybe you should make a correction here. This m will be k. Okay. So I mapped, because in gf to the power of k there are k basis vectors. Okay. There is this m is a wrong thing. So maybe you should correct it. So I mapped all the k elements here by this transformation. So now I want to check for t, because you can easily understand that this choice of t is crucial. Okay. Because this choice of t will essentially indicate whether the isomorphism property is satisfied. So again I apply the same trick what I have discussed previously. I calculate r alpha power of t. So remember that r is my target irreducible polynomial, that means the irreducible polynomial of my field of my target group. Okay. So therefore what I do is, I mean is essentially so r is the irreducible polynomial of the field gf2 power of k. So there I plug in alpha power of t. This should not be 0, but if I do mod of q by px, then I should get 0. Okay. Exactly in the same way as we have discussed previously. So now there will be exactly k primitive elements which will satisfy this condition. So this is an important criteria to help us prune and get the choice of t. Okay. So namely, you see that if alpha power of t will satisfy this equation, then alpha power of t whole power of 2j, 2 to the power of j, will also satisfy this equation, where j can go from 1 to k minus 1. Okay. So therefore note that of course the exponents are computed modulo 2 to the power of k minus 1. Okay. So why does this result follow? This result follows from this simple observation that if Rx is congruent to 0 modulo 0, I mean is congruent to 0, then in this field, because it is a characteristic 2 field, Rx square is also equal to 0. Okay. And likewise Rx to the power of any 2 to the power of j is also equal to 0. Okay. That means for all these k minus 1 values, immediately they will also become equal to 0. And if it is not equal to 0, then also these are not equal to 0. Okay. And therefore, right, we can actually do this, that we can easily, you know, like just check this condition. If this condition is not satisfied, because if this condition is satisfied, then we are done, we have got a value of t. But if this is not satisfied, then we can immediately rule out some possible t choices. We can actually rule out all these k minus 1 t choices, and actually with this all k, we can eliminate k t choices at once. Okay. So in order to do that, we actually maintain a data structure which is denoted as an array S. Okay. So this array S essentially stores all the possible values of t. Okay. So there are 2 to the power of k minus 1 possible values of t. So I indicate this by an array with 2 to the power of k minus 1 addresses and 1 bit of information. So, I initialize then this k cross k matrix T which I want to build up with each column indicated by Ti. So, there are k such columns. Okay. Note that interestingly the first column actually is already or at least one of the columns is already decided. So, this is what I want to essentially find out. So, note that the kth column essentially is 0 followed by 1 is already decided, because I know that 1 should get mapped into 1. Okay. So, if I have an element say 1 here, that should get mapped into 1. Okay. So, therefore, I should get the result also as 1. Okay. So, therefore, this essentially means that this column is already known. What we need is the remaining k minus 1 columns. Okay. So, in order to know that, what we do is a very simple evaluation now is we basically like choose T, that means we initially started with T equal to 1 and we just and we start with the primitive element in GF to the power of n whole power of m. Okay. So, note that although I have not told in details, but there are quite efficient primitive element or primitivity tests which are available. Okay. So, we can apply one of them and from there I can verify that whether alpha is a primitive element or not. You need not generate alpha and then check, you can do it more efficiently. Okay. So, therefore, what I do is now I essentially calculate R alpha power of t, and if this is equal to 0 then we are done. So, you can break this while loop. If not, then essentially you immediately you can strike out some possible values of s, I mean for some possible values of I by indicating that in the s array as 0. Okay. So, now when you go into the next parts inside the while loop, you just check whether st is equal to 0 or not, because if st is equal to 0, then that means it has been indicated as not a candidate by a previous run, or you check the GCD of t and 2 to the power of k minus 1. Now, you can easily verify that if the GCD of t and 2 to the power of k minus 1 is non-trivial and greater than 1, then t is not a candidate. Okay, because t is not, in that case essentially that violates its primitivity requirement. Okay. And therefore, right, you can increment t in that case. Okay. So, therefore, once you are passed through this, you should get a value of t, and once you have got a value of t, then what you just do is that for the remaining columns you just write the binary encoding for alpha power of t's. Okay. That means alpha power of 2t, alpha power of 3t and so on till alpha to the power of k minus 1t. You just find them and you just write the binary expansion of that. Okay. And that will give you this entire matrix. Okay. So, let me stop here. So, essentially the reference that I have followed is essentially this text. Okay. And you should be able to get more details in the book, and I am not really going into all the details, but I am trying to give you the major pointers. Okay. So, yeah, so hopefully, right, I mean you should be able to follow the remaining things from the book. So, to conclude, what we discussed in the today's class and also in the last class was we were trying to define field isomorphisms. We try to develop an understanding on these equivalent fields which are called as composite fields, and we also try to discuss conversion algorithms between the fields. Okay, like we try to find out efficient mappings between GF to the power of k and GF to the power of n power of m, and we shall see like in the subsequent classes how we can use these ideas to develop efficient architectures. Okay. Thank you.